Hello everyone, and how are you today? Well, I am here again, once again, for another week to talk about science. So let's get on to it. So today I'm going to be revisiting Cern. It's been a while since I've talked about Cern. Last time I talked about Cern, and the very first time I talked about Cern, was when I was talking about the God's particle. So, let's start the video. Ooh, sorry about that, guys. A little bit of error. So, what I was talking about before was, as I maybe about a month ago, had talked about Cern, and we was talking about the God particle. Well, today I'm going to be revisiting Cern, and I'm going to be talking about dark matter and a little bit of dark energy, because they almost are one in the two, but together, dark energy and dark matter work the entire universe, along with the God particle, which I'll briefly talk about. So, what exactly is Cern? So Cern is the Council of European Nuclear Research, and nuclear research is studying particles that are on the atomic level. This is like where nuclear fission comes in and how stars work, essentially, because stars fuel through nuclear fission, and that's how stars give off light and essentially fuel the universe. Well, their system of stars and planets that they host. So exactly, Cern has the Large Hadron Collider, and as you see right here in the picture, this circle symbolizes the entire Large Hadron Collider. This is a circular tube where they're shooting particles at very high speeds. And these high speeds are essentially what the particles needed during the time when the universe was being created, and how particles during supernova and explosions also can happen, because they have all this high energy and high particles just crashing into each other. So that goes into high energy physics, which is the study of the fundamental particles. And a way to think about the fundamental particles is that, like elements are the fundamental elements that make up our planet Earth, the fundamental particles is what makes up the universe and everything inside of us too, essentially. Because the universe is not made up of the atoms, well, of the elements that we have on this Earth, actually. Weirdly enough, everything we see, like stars and planets in the galaxy, only makes up for 5% of the universe, as you will see later on in these slides. And what else to talk about this, to briefly discern what the difference between a particle and matter is, because these are the two things that Cern is concerned with. Particles, you're able to describe their location, size, and their density, basically, depending on wherever they are in space. For example, like a coordinate system. This is how everything works in physics. You have to know where something's located in space. How are they able to physically know where I am, for example? Well, through my size, density, and mass. They're able to tell how much space I am consuming on a graph, essentially, and that's how big I am. Which also will contribute to how much gravity you work with. How much gravity you can pull into you, which is a big contender for dark matter as well. And matter, particles make up matter, and matter is basically what you're physically seeing. This computer's matter, I'm matter, and particles is what's making us up, essentially. So, what does CERN study? Well, they study, as I talked about, the fundamental particles, and here's the little periodic table, if you want to think about it, of the elements that make up the universe, which are particles, and they call this chart the standard model. Think of it as the ingredients that make up the universe. The God particle, as I talked about, or the Higgs boson, as you see right here. The Higgs is the boson that makes up all the particles in the world, because there's two different energy fields. There's a field that we can't see, which is the Higgs boson field, which is the Higgs field, and then they have the Higgs boson, which is in the Higgs field. And this boson, or the God's particle, is able to pick a particle that's in its field and give it mass. And now it's able to be detected in the physical realm that we're in. Because if you do not have mass, you're undetectable. And that is a problem that they're having with dark matter. Because we cannot see dark matter. However, we can feel it through its gravity. If you think gravity, if you want to think of how to feel gravity, if you sway wind and you feel a breeze, that's gravity. You didn't see it, but you know something was there. That's dark matter. And black holes. This picture right here is what was recently taken of the black hole at the start of this year, actually. Yes, this is the black hole that's at the center of our galaxy, the center of the Milky Way galaxy, and this is called Sagittarius A, because it's in the direction of the Sagittarius constellation. And this is at the center of the black hole, and around is space. The light here is what's being absorbed into the black hole, and then this is the black hole. And the line where the light and the black is separated is called the event horizon, where nothing is able to pass that. So what exactly is dark matter? Now, this picture right here, I did say you can't see dark matter, but you can feel it through its gravity. Therefore, dark matter is what holds things together like a glue in the universe. So stars wouldn't be able to form if they can't cluster and clump together. So dark matter is what's happening in this picture right here. As you see, these circles and these dots represent the stars that are trying to form and become stars. So, because not our solar system has one star, but many solar systems have more than one sun. It's actually kind of rare to have one sun. So this is eventually going to might become a planetary system. And dark matter is what's keeping these from separating from each other, or else they would expand away from each other, and we'll talk about that when we talk about dark energy. And why can't dark matter be seen? Well, everything is about light, whether it's UV light, infrared, radiation, gamma rays. Those are all types of light that we are able to observe in. However, us humans are only able to see in the physical, in the visible light. So as you see right here in this picture, white light has all the colors in it, and the object that you're seeing, you're only seeing that color because it's reflecting that light back to you in your eye. So our object is red because the red light was not absorbed and it's reflecting back into your eye, and that's how your brain registers color. So dark matter cannot reflect light, therefore we cannot detect it. It's like shining light on something black. It just, well, it doesn't absorb it like black does, because if dark matter absorbed light, you will be able to find where the light is and where the light went through physics. However, you're not able to, once light hits dark matter, they don't know what happens. They're not really sure what happens to it. It most likely, there's a third phase of light in here that I didn't put, and it's called a transmission, where it just shines through. If it shines through, then therefore you're seeing light, but when you're looking at dark matter, you're just looking at invisible black void. It's not even black, it's just basically invisible. And the third option right here is that it does not emit light, which means it doesn't create its own light to give off. And so these are the reasons why Cern wants to study dark matter, because if dark matter is what's holding everything together and we can't see it, how does it exist, why does it exist, and how can we determine why it is created? So, Well, I study dark matter. As I said, in this picture, it says normal matter that we can see as I was talking about is 4%. However, on some places on the internet, as I was researching, it says 5%. So numbers do vary by 1%. Dark matter, as I was talking about in the entire topic of this video, makes up 21 or 22% of all visible matter, and then everything else is dark energy. And you're probably like, what is dark energy? Well, that is on the next slide. So, astronomers, the scientists that study these kind of phenomenons, and physicists that are over there in Cern are studying dark matter, because dark matter is very important because the universe is expanding. After, like the Big Bang, everything goes poof and expands like this. However, if everything's expanding like this, we should be separating from each other, yet we're almost expanding together in a sense. So what's keeping us together is this dark matter. So, dark energy. As I was talking about light, you can see dark energy. And why is that you can see dark energy? Because it is what expands the universe, and everything is light. So therefore, if something's accelerating with you, as I'm talking about this Doppler shift, there's a red shift and a blue shift. A red shift is when something's getting far away from you and the light of it turns reddish. And that's because the red wavelengths are closer to you in space than the blue wavelengths right here, as the picture shows you. So therefore, red is more closer to you and you're able to observe it. However, if you see blue, it's coming towards you, and this picture is now reversed. And now blue is closer to your face, so that's what you're observing. And because of this, we're able to observe dark energy, because as everything expands, it's expanding with us, so the color doesn't change, so therefore we know it's dark energy, because compared to everything else around it and around us, that's either blue shifting or red shifting, depending on where and how you're looking at it. Dark energy doesn't change its color. It's the same no matter where you're looking at it. And that's what's so important. And it was discovered in 1998 by a type 1A supernova. There's two types. This specific supernova is two stars that are orbiting each other. One is really big and one's small. The smaller one is eating up this bigger one. So it's crumbling, falling apart, and dissolving, and almost looking like a black hole, but it's not. But this bigger, the smaller one is now getting bigger because it's consuming mass. And as you consume mass, you're creating more energy, and more energy means more heat. However, this smaller star is made of carbon, so it has a certain temperature before it ignite and explode. And this explosion shows us that the universe is expanding, because the colors should be changing differently as it's exploding. We should be seeing red and blue in different parts, because some will explode this way while others explode that way and explode this way. But because the universe is expanding, all of everything that just exploded expanded at the same rate and at the same time, so therefore it looks the same color. So that's, in a nutshell, how they discovered dark energy exists, and why all at the same time dark matter will exist too, because even though that stuff is expanding, it's still together in a sense. That's why you see these gas nebula clouds, because they're being held together still in a container, and they're going to dense up again and create stars. If that wasn't the case, everything would just keep expanding and no stars would be created. So, how does dark matter work? Well, as I said, you cannot, well, electromagnetism we're going to leave alone for the time being, because everything does emit electricity through magnetism. As I mentioned before, I can't remember in what video. It was shortly about how the poles of the Earth has not switched yet, and they're supposed to switch every 300,000 years, where the North Pole and the South Pole switch. So now the South Pole is the North Pole, and the North Pole is now the South Pole. And that's supposed to regenerate the Earth's energy field and protect it. However, dark matter does not have that. Therefore, that's why it does not interact with a lot of things. However, there's two ways you can interact with it. Through a strong force and a weak force in gravity. But all those are different types of forces, as well as electromagnetism, but that's not a part of gravity. I mean dark matter. So specifically, there are two types of dark matter. There is hot dark matter and cold dark matter. Now, what is the difference? As I've been talking about, it's hard to see dark matter. So if it's hard to see dark matter and it's hot, if something's hot, like in chemistry, the properties and the particles inside are like moving around, energized and fast, and moving extremely fast. Therefore, they're even harder to interact with because they're zooming fast. You can't do... So, with this energy, it's hard to attract something when you're moving fast because you don't have enough time to attach to something because you're just like brushing up past it, basically. But a weak force, well, yeah, weak forces are found in colder temperatures where it's much more chill, much more relaxed. You have time to get associated and bond to each other. This is what dark matter is all about. And this is where in cold, the particles are able to stick together and start forming into particles. That's what's so great about cold temperatures, is that life really comes from the cold, because space is honestly cold. Even though you see all that light, as I'm talking, the universe is expanding, and if it's expanding, there's a lot more space separating us. Therefore, light can only reach so far before you're able to feel the warmth. So space is very cold. However, this coldness, when dark matter is present, because dark matter is only concentrated in certain pockets of space where objects are taking place, ironically, because where there's a void, there's nothing like a planet or star, so therefore there's no need for dark matter to be there, because what is gravity going to be doing in a void? Interacting with itself. So the weak force is it's also when you're in close proximity where particles really interact the best, which is where I'm going to talk about contenders that can be dark matter. So I'll leave that for a little bit later in the video. Oh wow, we're reaching that point very soon. So what are we talking about? How do they know dark matter exists if we can't see it? Well, neon, which is very funny, because when I was talking about the God particle, to bring you guys up to speed a little bit, the God particle is basically a particle that is very hard to interact with because it doesn't have a charge to it. It's neutral. It's neither positive or negative, and everything in the universe has a charge to it. So if you're neutral, you're kind of just rubbing up and brushing up against each other. So it's not doing anything, and neon is something similar to that in this case. It is an inert gas, which means that its valence electrons are full, and therefore it doesn't want to interact with anything because it's basically neutral. So in this experiment, what they do is they have this tank full of neon, and when they shoot a particle inside, this scanner up here at the very top should light up if dark matter is present in the tank. And neon is very big as an element. It's the 54th element, and there's 100 and something elements, so they're increasing in size as the numbers are getting bigger. 54 also corresponds with how much it weighs, so think about 54 pounds. That's a lot of mass or matter for dark matter to be able to hit if it's present. And this is one way that they're trying to determine dark matter. So, possible contenders, as I was talking about, well, in the picture earlier, I'll put a little snippet here again so you can see the standard model. This neutrino right here is one of the possible contenders that can be dark matter because they interact on weak forces, which means they work best when they're in close proximity. So me and this computer are at a short distance, so therefore we're able to bond and be close to each other. But if we were farther apart from each other, because we're so small, we wouldn't be able to reach each other. So therefore, that's why dark matter can only work in close proximities. Why they think dark matter can work in close proximities, because it's so hard to see dark matter because it doesn't emit light or anything. And in this picture, you see two particles like they're doing at Cern with their Large Hadron Collider, shooting two particles at each other, and they are therefore studying what these particles shoot off. They might shoot off a God particle, they might shoot off dark energy, or they might shoot off any of these other types of particles. And what's so great, what these three right here are the core ones, that the core particles that later on decay, which is another way dark matter is observed, and the God particle is by radioactive decay, what they leave behind. So both the God particle and dark matter is hard to observe directly, so we have to look at what they leave behind or how they interact with something. So therefore, this is what Cern is up to with studying dark matter. These are the different, this particle right here, this very small one. See how small that neutrino is? These are like subatomic particles that are very hard to see. So this small neutrino is big enough, that neon is big enough to be able to allow it to hit if it's possibly there. So that's all that I wanted to talk about Cern and dark matter. However, during my research today, I found out that recently Cern is debating on shutting down their Large Hadron Collider because it is taking up too much energy in Europe. And because of the Russian-Ukraine war, they're not able to supply energy to European countries and other countries essentially, because Russia is a very big deposit for oil and giving out fuel to other countries. So therefore, Europe, Cern, who's in Switzerland, is having to shut down their Large Hadron Collider soon, until they're able to get past this energy crisis. And that could be a problem for Cern, because if they shut down for an energy crisis, we're at war. So how long are you gonna have your Hadron Collider and your research pause because we're at war? So that is all I'm here to talk about Cern. So hopefully Cern figures out this energy crisis. And I will talk to you guys later. It was great talking to you. Enjoy your day, and thank you for enjoying my session. Bye!